Welcome to the last lecture for General Chemistry 1. We're going to be covering Chapter 11. We're going to look at chemical bonding, Part 2, right? So in Chapter number 10, we talked about the Lewis model. Now we're going to talk a little bit about different theories, different other different models for how elements bind to make compounds. Let's just go and get started. Just to let you guys know, if you could, what might help during this lecture is if we were to get table 11.1 in our textbook as we go through these things. This way we'll be able to see the shapes. I'm going to post them. Obviously, they're going to be on the slide. But as I talk, right, it might just be easy to go through the table and what I am talking about. We can determine the shape of a molecule, right, by using what's known as I call it the VSPER theory, but it's actually VSEPR, the valence shell electron pair repulsion theory. This is based on the idea that electron groups repel each other, right, which makes sense because if you had an electron group, right, that charge is usually a negative charge, and you have another electron group, that charge is negative charge, and as we saw before, negatively charged things repel other negatively charged things. We talked about Coulomb's law, and we said that the farther apart the way that they are, the less energy that they have, and the better that they are. So this model is based on repulsion, right? How can we get the maximum amount of separation possible, right? Because we can't separate too much, otherwise we won't be in a compound. But we want, or in a molecule, but we want to make sure that we have the separation as possible. And what we're going to see is that determining what type of electron group and what we see will determine what shape that we're actually going to look at. Now, why do we care about the shape, right? Why do we care what the shape looks like in 3 dimensions? Well, because a lot of the pharmaceuticals that we use, a lot of the chemicals that we take in, that we use in everyday life, are solely based on geometry, right? It's solely based on what they look like. There are things in our body. I'm a biochemist, and so I worked with proteins, which are the machines, or some of the machines that are in our body. Well, some of these proteins are great targets for pharmaceuticals, but the only way that they're good that these pharmaceuticals will work if they have a specific geometry. If you look at aspirin, right? You take aspirin or ibuprofen, excuse me. If you take ibuprofen for pain, only 50% of what the pharmaceuticals that is in that pill is actually active, right? Has the right geometry for something to work, for it to work. And so, right. And so this is why this is very, very important. So this is why we're going to talk about it. So because of the repulsion, molecules can take distinctive shapes. And this is where we're going to look at table 11.1 will help us look at this. 2 electron groups. So one thing that we need to notice is we are basing these shapes on a central atom, right? We're focusing on the atom. On the left, it's beryllium. On the right, it's carbon. And what we see is that around that central atom, if a central atom is bound to 2 electron groups, notice I say electron groups, right? Because we will later on see that electron group can be another atom, or can be a bond, right? Can be a bond, or it can be a lone pair. And so if it's 2 electron groups, it's linear. I'm showing you CO2 here just to show you that the double bond will repel just like a single bond, right? And so there is no difference. A double bond acts as a single bond, as a electron group. 1 electron group for a double bond, 1 electron group for a triple bond. I just want to make that clear. So if there's a central atom with 2 electron groups, it is always linear, always linear. And I need to mention that we are talking about we're talking about electron geometry, right? Electron geometry. If you look at your table 11.1, we're talking about electron geometry. As you go through, you'll notice all of the electron geometries are exactly the same depending on how many electron groups are bound to it. We're talking about electron geometry here. I will change it up a little bit later when we talk about what's known as molecular geometry. So electron geometry. So now we had 2 electron groups, that's linear. Now let's go to 3 electron groups. 3 electron groups leads to what's known as a trigonal planar. Trigonal planar, planar because it lays flat, trigonal because it looks like a triangle. For the purposes of this exam, for the purposes of any exam, the bond angle for a trigonal planar is 120 degrees. You will need to know the bond angles. Bond angles for linear is obviously 180. It's a straight line. Now, what will happen is if we were to go into a lab, right, and we were to measure these bond angles experimentally, these bond angles will be slightly different, right? So we normally say 120. However, they might be 121.9, 116.2. You won't need to know with that specificity, but what we will need to know is 120 degrees. Okay, now we add a fourth group. Now we're starting, so the first three were planar, right? We're 2 dimensions, linear and trigonal planar. Now we add a fourth group to it, and we start to see our first 3-dimensional shape, and that's tetrahedral. Tetrahedral is, and the bond angles is 109.5. Notice, and I show this up here, we're going to talk about what it means to depict something on paper in 3 dimensions and how we can do that. You'll need that for lab, the lab where we do these molecular models. But if you look, there's methane, CH4, carbon tetrahydride, is depicted as we would draw it with a Lewis structure, accurate Lewis structure. However, in 3 dimensions, if we look at a tetrahedral, it looks nothing like that, right? It looks nothing like that square planar shape. It looks like a tetrahedral. So tetrahedral, 109.5 degrees. It's a central atom, in this case carbon, with 4 electron groups around it. Let's add a 5th, right? And so we add a 5th electron group. We get what's known as trigonal bipyramidal. Now, okay, let's think about what this trigonal bipyramidal means. Well, obviously, trigonal means there's a triangle in there somewhere. Well, if I were to rotate that trigonal bipyramidal, this molecule, phosphorus pentachloride, if I were to tip it on its axis and you were to look straight down it, what would you see? I want you guys to think about that. What would you see if I rotated this to where you were looking straight down the top chloride bond? Exactly. You would see a trigonal planar, right? You would see a trigonal planar. That's exactly what the equatorial, right? The middle chlorines or the middle atoms will be trigonal planar. What is the bond angle for something that's trigonal planar? 120 degrees. Exactly, right? So all the bond angles in that equatorial position are 120 degrees. Now, we added a little bit extra to it, right? Because we added those 2 chlorines in what's known as the axial positions. And so instead of having a trigonal planar, we have a trigonal bipyramidal. So if we were to imagine drawing lines from the equatorial chlorines to the axial chlorines, we would have a pyramid. We would have a pyramid on top, a pyramid on the bottom, and that's why we have a bipyramidal geometry. And that is 5 electron groups, okay, around the central atom. Let's add one more. We can do it. Let's add one more. And this is sulfur hexafluoride. And what we see is this is known as an octahedral geometry, right? Octahedral geometry. Every bond angle in an octahedral is 90 degrees. Again, if we were to tilt it, it would be a square, right? So it would be a square pyramid, and a square pyramid put together, that's an octahedral. There's 8 sides to it. And so what we have to know is the electron geometries of something with 2 groups, 3 groups, 4 groups, 5 groups, and 6 groups. And we are going to practice this in lab because the more practice that we get, the better it is. And so we do need to practice this, and we will practice this in the lab using models so that you'll be able to manipulate this yourself. Lone pairs, right? So we're talking about just electron groups. Now let's specify what group we're actually talking about, and that lone pairs on the central atom can affect the geometry, right? Because the lone pair is the most repulsive. A lone pair next to a lone pair is the most repulsive interaction there can be, whereas a lone pair bonding pair is in the middle, and a bonding pair is the least repulsive, right? Still repulsive, but the least. The electron geometry is not affected by a lone pair, right? Because the electron geometry we're saying is just electron groups, a lone pair is an electron group. However, molecular geometry is, and the example we use for that is ammonia gas, which is pictured here on the slide, right? I want you guys to draw, I want you to try this, right? I know the answer is there, and I know we've given you the answer, but I want you to try this. That NH3, right? NH3, I want you to draw the Lewis structure, and I want you to give me the electron geometry. And I also now want you to give me the molecular geometry, right? The molecular geometry, right? Because, and here's where those two differ. And this is why this table is very important in table 11.1. It's because it shows us the electron geometry, which doesn't change, but then it shows us the molecular geometry, right? And the molecular geometry, what it does is it subtracts the electron or the lone pairs, and all we're doing is looking at the molecule itself, right? All of the atoms that are bound. And in ammonia's case, let's go ahead and switch the sides. In ammonia's case, what we see is the lone pair goes away, and so all we're left with is a trigonal pyramidal, right? It's a trigonal because there's three molecules bound, and they look like a triangle, but it's not flat like a trigonal planar. It's a trigonal pyramidal. And this is where we kind of have to understand, right? Because if we're on an exam or something and we see NH3 and we forget the lone pair, then we have just drawn a trigonal planar molecule. But the molecular geometry is a trigonal pyramidal, right? And so this is why we have to understand these electron groups. This is why we have to understand Lewis structure and put it in conjunction with this. Lone pair is obviously more space. And so we said 109.5 for a tetrahedral arrangement. But if you look at ammonia, it's actually closer to 107 because of that repulsion from that lone pair. Now let's look at water, right? Let's look at water. Water's electron geometry is tetrahedral, right? Its electron geometry is tetrahedral, but its molecular geometry is bent, right? Is bent. And so the reason why is because there's two sets of lone pairs. Not only is it bent, but the bond angle decreases to 104.5. And so let's go ahead and look at just these three things put together. And then we're going to look at molecular geometries and different things about molecular geometries. So no lone pairs, it's 109.5. NH3, right, ammonia, had one lone pair, but again, with molecular geometries, we don't look at it, we don't use it for the shape. That's trigonal pyramidal, but look at the bond angles. It goes down to 107, and then water goes down to 104.5, and it's bent because it has two lone pairs. And so we just need to get comfortable looking at these things, looking at this, figuring different things out. Now let's go to that trigonal bipyramidal electron geometry, and let's start adding lone pairs into there. Now here's the key, right? Here's the key. When we talk about spacing, right, because we said it's really repulsive to have a lone pair, we need to put lone pairs in a place where they'll have the most space. And so here we're looking at we're looking at 5 groups with 1, 2, or 3 lone pairs. Lone pairs, when we talk about in this section with 5 groups, have to go on the equatorial position. They cannot go on the axial positions because there's too much what's known as steric hindrance. There's too much clash. They're too close to each other. And so they have to go in the equatorial position. So when we do that, we get one of my favorite shapes. So when we have 4 molecules or 4 bonding groups with 1 lone pair, we get seesaw, right? We get the seesaw pattern, the seesaw molecular geometry. That's my favorite molecular geometry. If we have 2 lone pairs, right? So we have 3 bonding pairs and 2 lone pairs, we get T-shaped. Notice this is not trigonal planar, right? Or trigonal pyramidal because of where the lone pairs are and the shape that they come from. Right, those two things combined will give us T-shaped, and really, what this is we just have to just do practice, right? We just have to look at these things. We have to figure them out, and like I said, we'll have a time in lab to do it. There's some practice problems for you to do, and so we'll get that taken care of. Make sure you guys have a lot of practice, and then if you have 3 lone pairs, then that shape is linear. Now let's look at 6 electron groups. with lone pairs. Now, the lone pairs for octahedral, for 6 groups, go in the axial positions and not at the equatorial positions. Just because instead of having, just variety of different reasons, for this case, you just have to trust me. This is what happens. There's less steric hindrance at the axial positions in this setup than there were in the other. And so here, what we get is, with one lone pair, we get square pyramidal. And with 2 lone pairs, we get square planar, right? Just like trigonal planar, only we add an extra group. So the question is, how can we draw 3-dimensional structures? Because we said, there's 3-dimensional structures. How can we draw that on paper? We can use what's known as dashes and wedges, right? We can use dashes and wedges. Now, we won't be using much dash and wedging here, in this class, but you will in organic, you will in biochemistry, just to denote the 3-dimensional shape of what these things look like, because that's very important. It's very important. And so the hashed wedge, or the dash, I call it a dash. If this was our page, a wedge points out towards you, a dash points back. And that's just what that means. And so I want you guys to practice. I want you to do ICL4 minus 1. ICL4 minus 1, and I want you to do CLNO, and what I want you to do is draw the Lewis structure, and I want you to tell me the shape, both the electron shape and the electron geometry and the molecular geometry of that. So again, we can use VSPER to predict shape of more complicated, right now we're just looking at one central atom, which is bounded to a few things. We can use this model, this theory, to predict more complicated ones. Now, I will have to define which atom I would want you to look at. But if I were to say, what is that carbon that's next to the nitrogen? What is that carbon's shape? Well, it's bound to 1, 2, 3, 4 different things. It would be tetrahedral. The other thing we can use VSPER for, and we need to talk about, is that molecular shape can affect what's known as polarity. We talked a little bit about polar bonds in the last chapter. And so, where there is a net negative and net positive charge. Well, we can look at vectors, and it's actually very well explained in your book on page. It's actually, a lot better explained in this book than it was in the 4th edition, on page 452 and 453. And I would just kind of look at that just so that we can kind of be aware of how vector addition, on how these things will work in 3 dimensions, and how we can see if something is polar. Because in the lab, this will be very important on whether, calculating if something is polar or nonpolar. And as we can see, obviously, if it's linear, it's nonpolar. Depending on the 3-dimensional shape, will determine if a more complicated molecule is polar or not. And so what we're going to do is we're going to end this here. We're going to end this here. And what we're going to do is I'm just going to briefly introduce. We are now going to enter into 2 more, a little bit more complicated, I don't want to say complicated, but just a little bit more, 2 more in-depth theories about how chemicals bind together to make molecules.